Ramanujan for G is now available on the Google Play Store. Try it out for free.
Welcome, friends. So, this is actually kind of towards the tail end of all the theory side of class 12. And I'm looking to aim to wind things down at some level. Mm, and so, this is like if you see Professor H.C. Verma's book, um, you know, Professor H.C. Verma's book, right? Um, then you notice that um, semiconductor devices is among the last chapters. The only remaining chapters are, of course, radioactive decay, which we have completed, and then special theory of relativity. you know um, I'm currently not going to look at special theory of relativity. I'm just going to wind down the work with the with the transistors, notably bipolar, right? Bipolar transistors. So in a bipolar transistor, this is the common emitter mode, right? BJT in a common emitter mode. The BJT in a common emitter mode acts as a amplifier. It's an amplifier configuration. The when people talk of differential amplifiers, they typically deal with uh, you know um, uh, another combination where there is not one BJT transistor but two, or very often four. you know and so that combination is beyond the scope of the material for this. We will look at the one combination, one transistor combination. Now when we say common emitter, basically in an NPN combination, right? There are two voltages. One is the voltage between the base and the emitter, and the other is a voltage between the collector and the emitter. Okay. Now the voltage between the base and the emitter is the input voltage, called the input voltage. Okay. Now an increment in that voltage is amplified on the output side. Okay, what does that mean? Means that the current on the output side is proportional, okay, at an exponential in an exponential way to the input. Okay, so you have an exponential curve, right? IC equals e to the power of minus VBE by VT minus 1. Okay, so although the current has an exponential relationship to the voltage BE, an increment in the BE leads to an linear increase in the current. So delta IC is a linear increment of the VBE. Okay, delta IC equals a constant times delta VBE. Okay, now that constant is amplified. So the delta VBE, if the delta VBE goes up so much, the delta IC will go up so much, and it will be a linear multiple of the increase in the delta VBE in that operating voltage at which you bias the transistor. Okay, so that's what they are saying in all this. So, but let me read this so that you understand what it is. In the common emitter or grounded emitter configuration, the input signal is applied between the base and the emitter, while the output is between the collector and the emitter. Okay, this type of configuration is most commonly used for transistor based amplifiers which represents the normal method of BJT, bipolar junction transistor. The common emitter amplification configuration produces the highest current and power gain of all the three transistor configurations. What are the other configurations? This is a common emitter. You can also have a common collector, and you can also have a common base, right? So, but this is a common emitter configuration which acts as an amplifier. Okay, now the output impedance is high as it is taken from a the in the front the impedance is low because it's forward biased. See, basically when they talk about forward bias and reverse bias, they a transistor consists can be thought of as consisting of two pretty much junctions, two diodes, right? So now when you connect a PN junction in the forward bias, which is a diode connected in the forward bias, right, the impedance will be low, right? In forward bias, we already looked at that. We spent a lot of time looking at the diode, right? So now the impedance will be low, right? So now an increment in the current will lead an increment in the voltage signal in the VBE, base emitter voltage, right? That incremental voltage will get amplified in the collector current. Okay, the collector is reverse biased. Okay, and therefore it has a high impedance. Okay, so the output impedance is high because it's taken from a reverse bias. Okay, so the IC is, so you have a VBE, which is a small voltage, and then you add a very small increment to that small voltage. Now the IC side, you expend a lot more power on the IC side. Okay, because you have to drive a load, right? So that load will be the current there is much more, and then you're using this VCC to kind of drive the whole power. So the voltage increment in VBE, which comes to which is synonymous to the IB times the resistance, right, give you the VBE, right? So the increment in the VBE is then becomes is a linear multiplied in the increment in the IC. Okay, so that's basically what happens in a transistor. Okay, so that's how you end up with amplification. Okay, so so this is the case of the base emitter is forward biased. Okay, and the so this is the base emitter is forward biased case. This is base emitter is not forward biased. This is a PNP. This is the NPN combination. So typically in the NPN mode, you have this amplification platform. Okay, so now the common base is a little different, right? So in the common base, the base is common, in the two transistors, and this is that has a high ratio of output resistance to input resistance, or more importantly, load resistance to input resistance, giving it a value of resistance gain. That is what is called a resistance gain. This type of transistor arrangement is not very common due to the high voltage gain characteristic. Its input characteristic represents that of a forward bias diode, while the output characteristics is that of the photodiode. Okay, so this is the common base system. An NPN connected in a forward base system. NPN, remember, not pointing out, therefore not pointing in. Okay, NPN is not pointing in, therefore the it's pointing out. What does not pointing in mean? Means it's pointing out, so the arrow points out, right? So now you collect the VIN in this way, and then you have what is called a resistance gain in terms of the resistance ratio, right? So that's how this one works. Then this is a PNP in a common base mode. Okay, so common base is not used commonly. Okay, the amplifier is the most common circuit used. Okay, so and now the this is the emitter current IC versus VBE. Okay, and note the exponent e to the power of VBE curve that is being drawn. So that for different VBEs, you'll have different curves, right? So now the output characteristics shows the relationship between the output voltage and the output current. Okay, so now in the common base situation, you have rather a very steady current, i.e., is ends up being a very steady current. Okay, so which is very different from the collector current was the common base voltage. Okay, so it's very different in that case. Okay, so so this is the typical combinations that are used. Common emitter is the amplifier combination, and the common base is a resistance gain combination, right? Then the common collector is also used somewhat, but again, it's not very important. So so learn the details of this, so you operate finally for the saturation region, right? The collector current is not totally cut off region. The emitter region is slightly reverse biased. Okay, the active region, cutoff region, and the saturation region. Okay, so those are the three regions, right? So um, I'm going to now move on to the last part of devices, and the last part of devices is um, deals with um, the gates. The device as a switch. Okay? Device as a switch is a very important idea. Because all of electronic devices begins, like much of what we use in terms of laptops and computers and everything, deals with using the transistor as a switch. Okay, now the most common form of transistor used in all these kinds of devices like the laptop and everything is not a bipolar transistor. It's not this NPN transistor that we discussed before. It which uses like these junctions, right? It uses with silicon with doping, right? So now actually they use what is called complementary MOS, right? Complementary metal oxide semiconductor. Okay, so CMOS is the most common form of transistor used, and CMOS does not have an exponential voltage to current relationship. Instead, it has a polynomial relationship. Okay, and so CMOS can also be used as an amplifier, but most often CMOS technology is used. There is a CMOS consists of an NMOS and a PMOS. Okay, combination of a NMOS and a PMOS makes you a CMOS. Okay, now in a we had two junctions, back-to-back junctions, a NP and a PN, right? In a bipolar transistor, right? And then we went on to look at the middle region is very lightly doped. This is called the base, right? The other sides are heavily doped. One side is, and that side is called the emitter. Heavily doped side is the emitter. The slightly less heavily doped is the collector, right? And therefore, we had the combinations associated with that. So NPN is the combination. This side, this was the PNP. We discussed this before. Now, this time we are going to look at the case. I'm not doing the recap for you, and then we discuss the BJT as an amplifier, where the collector current is amplified in relation to a slight increase in the base emitter voltage. Then it's that collector current it then flows through the load resistance, which results in a bigger voltage drop across it, right? So the voltage across, the bigger the current, the bigger the voltage drop across the RL, right? So that is how transistors work. Now we can also use this is when the transistor is used in the saturation region, right? But then when the transistor is used in the cutoff and active regions, in the cutoff state, it is off. Nothing happens. There's no current flowing through, right? Then when it goes to the active stage, it is on. Okay, so this process of switching from saturation and cutoff, between saturation and cutoff, rather than active, right? The previous case we were working on the active region, right? The slope, right? So now instead of working on the active region, you're either on or off. You're on when you're in the saturation region, and you're off in the cutoff region. Cutoff region, there is no current. Okay, so that's what happens in the case of a transistor. Okay, so now you have you have two inputs, and then you have one output. Now one input determines whether you pass through or not. Okay, so now the transistor will become on when a sufficient V voltage is given to the input. Okay, so when a sufficient V voltage is given to the input, the other input will either be passed through or it will be cut off. Okay, so now these two, there are thus two inputs to the gate. When a transistor is used as a gate, typically there are two inputs. Okay, when those two inputs, some combination of those two inputs produces the resultant output. Now there are two types of gates, right? So look at this. So here the transistor is on, right? The IB is there, the transistor is on, right? And therefore you have whatever voltage you're applying just passes through. Okay, so whatever voltage here you're applying just passes through. In the second case, in the off case, right, the transistor is off, right? And therefore, whatever voltage you're applying does not pass through. Okay, so that is the simple explanation for what is called a logic gate. Okay, now there are five different types of logic gates. Okay, but this is a very this is what is they use what is called Boolean algebra. Okay, now Boolean algebra, when they make Boolean algebra, a Boolean algebra is similar to um, the operations that you perform, like when you do set theory, right? You do set theory, you have union and intersection, right? In your mathematics, right? So like that, in Boolean algebra, a zero or a zero produces a zero. A zero or a one produces a one. A one or a zero also produces a one. So the gate is that produces this result is called an OR gate. A one or a one also produces a one. So if one of them is a one, the result is a one. If at least one of them is a one, the result is a one. Such a gate is called an OR gate. A second gate is the AND gate, when both have to be one for the result to be one. Okay, so let me show you, draw you these diagrams. Okay, so this is the shape of an OR gate. This is an OR gate. And so for each gate, there is what is called an associated truth table. If both inputs to an OR gate are zero, the resultant is zero. If at least one is a one, if either A or B is one or both are one, the resultant is a one. So the three cases when so one case when it's a zero. So this is an OR gate. The other gate with three inputs is an AND gate. Okay, then this gate is the NOT gate. If A is zero, it produces a one. If A is one, it produces a zero. Many children are like that. You say yes, they'll say no. Stubborn children, they are the NOT gates of the world. Now, the AND gate, in the AND gate, both A and B have to be one for the resultant to be one. If even one of them is zero, the resultant is zero. It's like when you have to have a veto vote. When both A and B have a veto vote, then if both of them say no, one of them says no, it's a no. You need both of them to say yes for it to be a yes. So this is a AND gate. Now, finally, there are two other gates called NAND gates and NOR gates. A NAND gate is a AND gate followed by a NOT gate. So notice the output here 0 0 0. You pass that through a NOT gate, you'll end up with a 1 1 1. If you had a 1, you will end up with a 0. So you take this and you add a NOT gate at the end, you will end up with a NAND gate. The NOR gate is similar. You take an OR gate and add a NOT gate at the end, and you will end up with a NOR gate. Now, in reality, lot of the logic circuits used in electronics mostly use just a NAND gate. You can synthesize everything in the logic of most digital electronics using just a NAND gate. Sorry, not this one, not a NAND gate, but a NAND gate. A NAND gate can be used to synthesize both a NOT gate, an OR gate, and a NAND gate. Instead of using three different types of gates, they mostly use only one gate, one type of gate, which is the NAND gate. Okay, this is the truth table of the NAND gate. So you should understand each of these gates. Okay, and I went through all of them so that you do understand how these logic gates behave. Logic gate is a simply a transistor. Now there is another kind of use for these transistor systems, which is to store data in the device when it's on. Okay, so such a device is called a memory. It stores a value. So if you had something, whether the value is 0 or 1, so that value is stored in memory. Okay, if you learn computer science, you will note that it is a combination of logic and memory that facilitates computing. So what is memory? Memory is a location, is an electronic location which stores data. There are two types of memory. There is hard disk, which stores data permanently. Then there is random access memory, which is there in a device like this, which when the device starts up is ready to store memory. Then memory is stored in the form of gates, which are called flip-flops. Now, there is something called a clock. Okay. Now, the clock is passed into these various gates, and when and it happens like lockstep. Okay, now when the clock is passed, then you have these logic elements come on or come off. Okay, so using this, you have, and as a result, the result of every operation happens on a clock, and the clock goes to every logic gate in the system, so that everything happens at lockstep. Okay, so there is a clock as well. Therefore, you have waveforms which are then part of that. You have waveform analysis. So let's say here you had a gate. Okay, let's say you had a NAND gate, right? So now the input is taking this form. A is taking this form. The input B is taking this form. So what will be the output? It's a NAND gate, right? A and A both are 1. The output will be 0. Both of them are 0, so the output will be 1. One of them is 0, the output will be 1. Because it's a NAND gate, right? You just take the truth table and then you look at the values. See, this one is 1, right? Here, this one is 1. A is 1. B is also 1. So 1 and 1, output is 0. That will be Y. For in this, in this time period, right? T1, 0 and 0, output will be 1. Okay, so you have a timing diagram. This is a timing diagram. Okay, time t equal to 1, this is the value of A, this is the value of B. What is the output, right? So so this clock is passed to every circuit in the microprocessor, okay, or every circuit in the particular chip. Okay, and when this clock is passed, it then so on that clock you have various results for at each period. Okay, and so this is a conceptual understanding of it. In reality, things aren't so square, they are kind of like that, and that's why you have to be very careful in setting the clock and setting the results, and yet it all seems to work quite magically in circuits. So now here's a quick quiz. Okay, the given electronic network is equivalent to what? Okay, the first is a NOR gate. Okay, the second is a NOT gate. Okay, so you have a NOR and a NOT. The result of a NOR is it's an OR and a NOT. The NOT of a NOT is the same thing. The NOT of a NOT is the same thing, right? So two NOTs in series negate each other. So the first is an OR followed by a NOT. So the result is also just a NOR gate. Okay, so this takes some practice also. Okay, learn about truth tables, learn about the truth tables of this. And the other way to solve this is you can draw a truth table for this whole circuit. Okay, so you can call it is like black box. You can treat the whole circuit as a black box. Then you say A has one value, B has one value, what is the output? Okay, so now if you draw the result A and B, then look at what is the if you say 1 and 1, what will be the output? It will be, if it's a NOR gate, is it's what? It will be 0. Okay, so like that you can calculate the output in each case, give it a value 0 and 1, give it a value 1 and 0, give it a value 1 and 1, and then you will end up with a gate. Then you see which gate it is. Okay. Boolean algebra in some ways is what is called, has follows a closure property, in that the all these produce all the results that you do that you can ever expect. So there is exhaustive in that sense. Okay, so to get output for the following circuit, the correct choice for the input is what? How do you get this circuit to produce a 1? This circuit will produce a 1 when C is 1. That much you know, right? You need both this and this to be 1. Therefore, C has to be 1. The only one where C is 1 is this one, right? So here A or B, right? Here, at least one of them has to be 1. So here A or B is 1. So let's choose only 3. Okay, this is a quick quiz. Okay, so what I want you to do is I want you to spend some time understanding these logic gates, studying the chapter in HC Verma or your NCRT textbook. NCRT textbook is a very good textbook also. And then I did 2 small problems. I want you also to do some problems. And on top of that, I want you to understand, read the chapter about this transistor configurations, and then understand all these common emitter, common collector, and then look at how NPN transistor can be connected so that it can act as a amplifier. Okay, so you must keep it simple, because we are not trying to teach you everything that you would learn uh, um, in an undergraduate electronics class or electronic degree for that matter. We're trying to teach you just enough to survive these problems, but then you must learn what you learn well. So learn about truth tables, learn about gates, learn about clocks, and understand it conceptually, and finally, most importantly, also learn about common emitter, common collector, NPN, and bipolar junction transistors. Then do some problems. This material will carry some marks for you. Okay, maybe I don't know whether it's 2 questions or 3 questions. Whatever it is, get on top of this material, because it's not that difficult. Okay, once you understood the more complicated material, this material involves a lot of learning. And so spend a lot of time learning this. Do some truth table questions. There are a lot of truth table questions you can go by. Get the JnanaMarga. If you're taking JE, get the Ramanujan app. Taking NEET, get the Sushruta app, and using them, do the assessment associated with these questions. Okay, so with that, I'm going to stop, and then we will continue starting next week. What I'm going to do is I'm going to start with a short um, refresher, followed by problems. Refresher followed by problems. Refresher followed by problems. Okay, and but then I expect you to have mastered the material starting next week. And of course, there will be time for Q&A. Okay, so at the end of the class, I want you to ask your questions or send me the questions ahead of time, and I'll deal with them in the class. Okay, so with that, I'm going to stop, and then we can look at material starting next week. But this week, this is where I want to end. Okay, so thank you, and I'll see you again next week in the new year. Happy New Year.